Welcome dear students once again, and in this video now we are doing congruences, we are doing residue systems. In the previous video we have discussed several properties relating to residue systems, and now what we are going to do is complete residue system modulo n, reduced residue system modulo n, non-negative residue system modulo n. These things we are going to discuss in this video. So let us first of all define complete residue system. What a complete residue system is. Modulo m, obviously, for some integer m we will define complete residue system modulo m, and in short we will write it as CRS modulo m. CRS modulo m means complete residue system modulo m. What a complete residue system modulo m is? A set S of m elements x1, x2, x3, xm is said to be complete residue system modulo m if any one of the following two properties is satisfied. If either xi is not congruent to xj modulo m for I not equal to j belonging to the set 1, 2, 3 up to m. That means no two elements of this set are congruent to each other modulo m. Either this property is satisfied, even then it will become a complete residue system modulo m, or for every x belonging to z, the set of integers, there exists exactly one xi in the set S such that x is congruent to xi modulo m. So if a set of m elements has either this property or this property, then it will become a complete residue system modulo m. Secondly, leave that you don't know how many members are there. One thing is sure, that a complete residue system modulo m will always have m elements. But suppose you don't know how many elements are there, but these two properties both are satisfied. Even then, the set is a complete residue system modulo m, and it will have definitely in that case m elements. So this is the definition of complete residue system modulo m, and let us exemplify. Let us have an example to have more clear idea about complete residue system modulo m. Suppose I am having m to be 11. I am having m to be 11, and I am writing a set S. A set S as suppose I am writing here 11, then I am writing 23, then I am writing 35, 3, 4, 27, 39, 40, 19, 20. This set I have written 20, and one more. How many elements are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. One more is required, so I am writing 43. How many elements are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we are dealing with modulo 11. So one thing is okay, it is having 11 elements. Now if no two members of this set are congruent to each other, then it is a complete residue system modulo M. And it is the case. You take any two elements from this set, you take suppose 23 and 39, then 23 is not congruent to 39 modulo 11. This is just to exemplify. You can take any two elements and they will not be congruent to each other modulo 11. Secondly, if you see, if you take any number, any integer in fact, then it is congruent to exactly one number from this set modulo 11. So for example, let me have one number. What number I am taking? Let 106 be there. 106 is an integer and 106 is congruent to exactly one member of this set. Exactly one member. Let us see which member it is. So 106 is congruent to which member here? Modulo 11. It is not congruent to 11 because 106 minus 11 is 95 and 11 does not divide 95. So it is not congruent to 11. It is not congruent to 23 also, because in that case 106 minus 23 is 83 and 11 does not divide 83. If you take 35 here, then 106 minus 35 is 71. 11 does not divide 71, so 35 cannot be here also. If you take 3 or 4, 106 minus 3 or 106 minus 4, 103 or 102, both are not divisible by 11. So 3 or 4 cannot be here. If you take 27, the difference will become 79. And 79 is also not divisible by 11. So 27 will not be there. What about 39? If you take 39 here, the difference will become 67. 11 does not divide 67. So 39 cannot be here. What about 40? 106 minus 40, it is 66 and 11 divides 66. So 40 is here. Let us check the rest also. 19. 106 minus 19, it is 87, not divisible by 11. What about 20? 106 minus 20, 86, not divisible by 11 again. What about 43? 106 minus 43 is 63, not divisible by 11. So what you have taken an arbitrary integer and it comes out to be congruent to exactly one member of this set. That makes this set a complete residue system modulo 11. This is just an example. You can take any integer and every integer will come out to be exactly congruent to one member of this set. So this is a complete residue system and it is a property. One more thing. I am going to construct another set. Let it be S dash. What I am going to do now, I will divide each of these elements by 11 and write the remainders only. 11 divided by 11 and remainder will be 0. 23 divided by 11, remainder will be 2, 1. 35 divided by 11, remainder will be 2. Similarly, you will get 3, 4, 5, 6, 7, 8, 9 and 10. So these will be the remainders obtained when you will divide these quantities by 11. This is also a CRS. This is also a complete residue system modulo 11. And not only this is the complete residue system, but it is the least positive complete residue system modulo 11. Obtained from a complete residue system by dividing each member by 11, or you can say M if you are dealing with modulo M, and just write down the remainders. You will get the non-negative complete residue system modulo that particular number. So what is the difference between a complete residue system and a least positive complete residue system is very much clear here. And once again, each member here will be exactly congruent to one member from here. So if you are having any two complete residue systems modulo M, then exactly one member of the first set will be congruent to exactly one member of the second set. So these are the definitions, and then let us take some examples, some questions, some theorems, and then I will move on to the next topic, that is reduced residue system modulo n. So one question, if A1, A2, A3, AM is a complete residue system modulo M, then and K is an integer such that GCD of K and M is 1, then KA1, KA2, KA3 and so on, KAM is also a complete residue system modulo M. This we have to prove. This is given to be a complete residue system modulo M, and this we have to show that is also a complete residue system modulo M. Note that how many members are there? KA1, KA2, KA3, KAM, so exactly M members are there. And if you are having exactly M members, then either of the two conditions are to be checked. Either you show that for every integer x there is exactly one member here which is congruent to x modulo M, or you show that no two members of this set are congruent to each other modulo M. Either of the two conditions will show that this is a complete residue system modulo M. So I will take the second one. I will prove that no two members of this set are congruent to each other modulo M. And this I will prove by the method of contradiction. First I will suppose that there are two members which are congruent to each other modulo M, and then we will arrive at some contradiction. That will mean no two members of this set can be congruent to each other modulo M, which means this set is a complete residue system modulo M. So let if possible there be two members of this set KAI which is congruent to KAJ modulo M for some, definitely I is not equal to J, but both belong to this set 1, 2, 3 up to M. Suppose two members are congruent to each other modulo M, and this will give you that M divides KAI minus KAJ. A is congruent to B modulo M means M divides A minus B, and K can be taken out common from here. So take out K common, you will get AI minus AJ. You know that if A divides BC and GCD of A and B is 1, then A divides C. The same situation is lying here. M divides K times this quantity, but GCD of M and K is given to be 1. That means M divides this quantity. So you will get M divides AI minus AJ. And once again write it in the congruence form. You will get AI is congruent to AJ modulo M, which is a contradiction. Why? Because AI and AJ are the members of this set, and this is a complete residue system modulo M. No two members of a complete residue system modulo M can be congruent to each other modulo M. So how AI and AJ members of a complete residue system can be congruent to each other modulo M? This is not possible. So we arrive at a contradiction. And why this contradiction is there? Because we have supposed that two members of this set are congruent to each other modulo M, which is not possible therefore. And if there are M members in a set, M integers, which are not congruent to each other modulo M pairwise, that means this is a complete residue system modulo M, which we wanted to prove. So we have proved this question, we have solved this question, and next I'll prove another very important result, another very important theorem related to complete residue systems. So let us see what it is. Theorem. Let m and b integers, positive integers, with GCD of m and n is 1, let x1, x2, xm and y1, y2, yn be complete residue systems. This S is for systems, complete residue systems modulo m and modulo n respectively. That means I have taken this set, I'll name it as S and I'll name it as T. So S is a complete residue system modulo M and T is a complete residue system modulo N. Then this set M times Xi plus M times Yj, where I is running from 1 to M and J is running from 1 to N, is a complete residue system modulo Mn. This we have to prove. So what I will prove? I will prove two things. First of all, I will prove that this set contains exactly Mn elements. And secondly, I will show that no two members of this set are congruent to each other modulo Mn. And that will be enough to show that this is a CRS modulo Mn. Look at how many choices are you having for this Nxi. That means the number of choices of I, and the number of choices of I are M. So here you can have M choices. Similarly, here you can have N choices. And for each choice here, you are having N choices here. So how many total number of choices are you having here? Mn. So how many members this set is having? This set is having Mn elements. So if you are saying this set as A, then number of elements of the set A is equal to Mn. This set is having Mn elements. And what rest is to prove that no two members of this set are congruent to each other modulo Mn. And this again we will prove by the way of contradiction. First we will suppose that there are two members which are congruent to each other modulo Mn, and then we will arrive at some contradiction. So suppose if possible, there are two members. One is Nxi plus Myj, which is congruent to Nxi dash plus Myj dash modulo Mn. I suppose that there are two members in this set which are congruent to each other modulo Mn. And I'll arrive at some contradiction proving that this is not possible. And this is not possible means a set of Mn elements having no two members congruent to each other modulo Mn means the set is a complete residue system modulo Mn. Look at from this. You can write that Mn A is congruent to B modulo C, or A is congruent to B modulo M. That means M divides A minus B. So A minus B is Nxi plus Myj minus Nxi dash plus Myj dash. Also, we know that M divides Mn without any doubt. Mn is a multiple of M. M divides Mn and Mn divides this number. So that means using transitivity you can directly say that M divides this number. So I am not writing the new step, I am directly writing here that this means M divides this number. And M divides A minus B means A is congruent to B modulo M. So once again I am writing Nxi plus Myj is congruent to Nxi dash plus Myj dash modulo M. And we know that if we are working with modulo M, then from the congruence equation every multiple of M can be removed. So MYJ, which is a multiple of modulo M, can be removed. So you will be left with this one. And similarly, MYJ dash is a multiple of M. So from the congruence equation, you can remove it. And now from this congruence equation, you can write M divides NXI minus NXI dash. So this means M divides N times XI minus XI dash. But GCD of M and N is 1 given here. Now A divides BC and GCD of A and B is 1, so A divides C. So from here you can write M divides XI minus XI dash. And this means XI is congruent to XI dash modulo M, which is a contradiction. Why? Because Xi and Xi dash are the members of a set S, which is a complete residue system modulo M. In a complete residue system modulo M, you cannot have two elements which are congruent to each other modulo M. So it is a contradiction. And why this contradiction? Because we have supposed that two members of the set A are congruent to each other modulo Mn. So it cannot be, it is not possible. So no two members of A can be congruent to each other modulo Mn. And how many elements are there in the set A? Exactly Mn. So a set of Mn elements having the property that no two members are congruent to each other modulo Mn makes this set a complete residue system modulo M. So this we have proved, and I am going to stop this video here. In the next video we will discuss the reduced residue system modulo M. Till then, thank you once again.